Okay, we're going to do the page 21 and 22 of differentiation. Um, we'll do every other one. So given A equals 1/2 LB and 3L minus 5B equals 18, express A in terms of L. Okay, so A in terms of L, that means we have A on the left, and on the right we have just variable L. Well, we got this variable B here. So how do we get rid of the variable B? Well, we use the constraint equation because the constraint equation relates B with L. So all we need to do is say, hey, B equals something, something, something with L in it, and then we'll substitute in for B and get rid of it. Okay, so we start with the equation here, 3L minus 5B equals 18, and we're going to put it in the form B equals blah, blah, blah. So the first thing we're going to do is we're going to try to isolate the B here by moving the 3L's to the other side. So we subtract 3L from both sides. And then we end up with negative 5B equals 18 minus 3L. Now we're a little bit closer, right? Now how do we get B by itself? We're going to divide both sides by negative 5. And then we'll get B equals 18 divided by negative 5 minus 3 times negative 5L. So this will just become positive, right? So it's negative 18 fifths plus 3 fifths L. Oh, and I forgot, where did my 3L go? Oh, there it is. Okay. So we got B is equal to this. Now we're going to take this and we're going to put it in for B. So now we have A equals 1/2 L, and then B is actually equal to negative 18 fifths plus 3 fifths, which is actually 0.6 L. Okay, so we have expressed A in terms of L now. Then it says find the minimum value of A and the value of B that corresponds to this minimum value. Okay, now to find the minimum value of A, they might expect you to use the derivative. Since we have the calculator, we could just put the equation, this equation, A equals 1/2 L minus 18 fifths plus 0.6 L. We're just going to put in the calculator. Instead of L, we're going to use X. And instead of A, it's Y1. Okay? So, and remember, 1/2 is the same thing as 0.5, and it's a lot easier to put in without worrying about parentheses. So I'm going to do that. And then I do parentheses, negative 18 fifths. I can just do that as a fraction. Then don't need to simplify it. And then 0.6 L, 0.6x. Okay. All right, the formula is in there, and then I'm going to graph it. And it says find the minimum value of A and the value of B that corresponds to this minimum value. So let's say we'll do second calc because we want to know where the minimum is. And we'll say minimum, and the left boundary is there, and the right boundary will be slightly to the right. And then we'll guess. And it'll tell us that the minimum coordinate point is 3, negative 2.7. So the minimum point, the y value, is equal to negative 2.7, and that's what they were asking for. They were asking the value of A, which happens to be y1 in the calculator. So there it is. And what's the value of B that corresponds to the minimum point? Well, there's a formula here, which says B equals this, okay? And then I'm just going to substitute in for the B. Remember, this is the same thing as 0.6 L. I'm going to substitute in for L negative 2.7. Negative 2.7. And I can just put that, you can do that with the calculator. I can put negative 18 fifths negative 18/5. And then I'm going to add 0.6 times negative 2.7. Negative 2.7. And my answer is negative 5.22. Okay, so that's B that corresponds to the minimum point. Okay, let's go on to 13. Given 3y plus x equals 30, find the minimum and maximum value of 2xy and determine its nature. Okay, so they want to know the minimum max of this function. Unfortunately, this function has two variables, x and y. So we need to find out what this is equal to, and let's just call it a because they never called it anything. We want to find what the maximum or minimum value of a is. Unfortunately, a is depending on two different variables, so we're going to use the constraint to try to eliminate one or the other variable. Let's see. What if we put x equals by itself here, because it's the easiest thing to do. We subtract 3y from both sides, and we'll get 30 minus 3y. And then we'll put that into here, and we'll have 2 times 30 minus 3y times y. And we can put that in our calculator, and then we can see if it's a maximum or minimum value that's going to be in this function. So we're going to put 2 times 30 minus 3y, and instead of y we're going to put x because that's the only variable in the calculator. And then we multiply that times y or x again. And then we graph it. It's going to give us a quadratic. We can't really see the whole quadratic, but it looks like maybe it's like turning over there. So let's do zoom fit. Zoom fit, which is option 0, is always good when the thing goes off the edge of the page. There we go. Zoom fit is 0. Okay, there we go. Now we can see the very top of it also. And so now we know of the maximum minimum, it's a maximum. Okay, and then it asks us for the maximum value. So what's the maximum height here? Well, we can find that by doing second calc, maximum, and then we'll say left bound, that's fine, and then we go to the right of the maximum value, and we mark it, and then it will estimate where is the maximum value. Any guess is fine. So the maximum is 5, 150. And this is equal to a, we named it a. And 5 is the y value, right? The y value. So y equals 5, a equals 150. So they wanted the maximum value of this whole function, which I just called a. So we'll say it's 150. And determine its nature. Well, we already found out it was a maximum, so that's that. Okay. 17. Given that r plus h equals 6, express r squared times h in terms of r only. Hence, find the maximum value of r squared h subject to the constraint r plus h equals 6. Okay, so let's just call this a because they don't tell us any other name for it. So we have a equals r squared times h, and it says find this expression in terms of r only. So we need to get rid of the h. How do we get rid of the h? Well, this constraint relates r and h. So what if we subtracted r from both sides? Would that help? Subtracting r from both sides leaves us with h equals 6 minus r, and we've kind of solved our problem. We can substitute that in. We'll have a equals r squared times 6 minus r, and we've just gotten rid of the h. So we do have it in terms of r only. So that's the first answer. Hence, find the maximum value of r squared h subject to the constraint r plus h equals 6. So they want to know what is the maximum value of this. Well, we could just graph it on the calculator, and then we'll find it. So r squared would be x squared, because there's no r in the calculator, 6 minus r. And we'll graph it, and we will see that it is a Oh, it's not a quadratic, it's a cubic. Okay, and now we need to find the maximum value of r squared h. So it looks like there might be a maximum there. Let's do a zoom fit, which is option 0, to try to get a better look at that. Yeah, it's kind of hard to see. I think it's like right there. How about if we blow it up a little bit? So the window size, instead of Ymax 1600, I'm going to put Ymax positive 400. There we go. We can see it a little bit better now. Now let's find the maximum value. We can find the maximum value by doing second calc, because that's going to find us maximums and minimums. And the left bound there is fine. Go to the right. Guess that's fine. And the answer is 4, 32. So our coordinate is 4, 32. Now what's 32? That's A. We just named it A. And 4 is going to be R. Okay? And they want to know what's the maximum value of r squared h, which is A, so the maximum value is 32. Okay? Now a couple more problems on the last page. Now the hint I'm giving you is draw a diagram first when you have a word problem. A gardener wishes to enclose a rectangular plot of land using a roll of wire netting that is 40 meters long. One side of the plot is to be the wall of the garden. Okay, so let's say you got a wall, and the gardener is going to make a garden or a plot, a section of land using fence. And the total amount of fence is 40 meters. Okay? One side of the fence is the wall, so you only use 40 meters for 3 sides of the wall. How should he bend the wire netting to enclose the maximum area? Okay, we're going to have to make some variables here. Let's call this the width, and this the height. And then let's find the area, because it says maximum area. That's the variable we want to maximize. It depends on W and H, right? Because the area is W and H. Okay? Now, unfortunately, we have the variable we want to maximize, and we have 2 variables over here. The only way we can figure out what the optimum area is if we eliminate either the W or the H. How do we eliminate the W or the H? Well, look here. We have something that can relate W to H and the length 40 meters. It looks like if we add the 2 W's and an H, we should get 40, because that's how much fencing we have. So that's the same thing as 2W plus H equals 40. And let's solve for H. Get 40 minus 2W. And then now we can substitute that in here, and we'll get A with only W's. Now we have A just with W's. And now we can graph that. And when we do, that is going to, instead of W, we have to put X, right? 40 minus 2X. I'm going to graph it. And it's going to be a quadratic. And whoop, it's going off the screen. So we can adjust that by changing the window size. So the X max, let's change it to something like 100 so that we can see more. Okay, so we'll do second calc, and we're trying to find the maximum. And so the left bound, let's try to go, oh, there's the cursor, and then we're going to go a little bit to the left of the maximum, we hit enter. We go a little bit to the right of the maximum, we hit enter. And then we guess, and then the answer is going to be 10, 200. Okay, and what was this again? This was W and this was A, right? So how should he bend the wire netting to enclose the maximum area? Well, the W should be 10, and the H should be 20. That would give you an area of 200, which apparently is the maximum possible one. Okay, we'll go to number 5. A long strip of metal 120 centimeters wide is bent to form the base and two sides of a chute. A chute is like it's like a big square tube, or a rectangular tube, with a rectangular cross section. Okay, find the width of the base that makes the area of the cross section a maximum. Okay, and again, I'm going to draw a diagram because that helps. Okay, it says a long strip of metal is 120 centimeters wide, is bent to form the base and two sides of a chute with a rectangular cross section. Find the width of the base that makes the area of the cross section a maximum. Okay, so what you have is you got like a piece of sheet metal, it's 120 wide, and we're going to bend it into a U. A chute could be an enclosed rectangle, or it could be an open rectangle like this one. So what they're doing is they're saying, hey, this purple area here, this purple line, this plus this plus this is equal to 120. Okay, I'm going to erase this misleading drawing that makes it look like it's a closed rectangle. Now let's try to write equations for this. So we want to make the cross section a maximum. The cross section would be this area here. The cross section, let's give it as A. So A is equal to, and I'll call this width, and I'll call this height, and I'll call this height. So the area is width, height times width, right? And then I can relate H to W by saying, hey, H plus W is equal to 120, right? Or 2H plus W equals 120. And I want to optimize A. I want to make it maximum possible. So let's get rid of either the H or the W. It's easier to get rid of the W. By subtracting 2H from both sides, we get that. And then we substitute the W in there, and then we get H times 120 minus 2H. And now we have an equation for A just in terms of the H variable. And so now we can put that in the calculator, and we can change the H to an X because there is no X in the calculator. And we'll put 120 minus 2H, or 2X. And then we'll graph it, and we'll get a quadratic. We can't see too much of it. Maybe we should do zoom fit, which is option 0. Oops. Zoom, option 0, and there it is. Okay, and then it says, find the width of the base that makes the area of the cross-section a maximum. So when is the area maximum? It's right there. We'll do second calc, and then, second calc, I say. And we'll try to find the maximum, which is option 4. Oops, wrong place. I did the left bound in the wrong place, so I'm going to have to go back and start over again. Maximum 4, and then I'm going to do the left bound. We've got to move to the left side of the max, and then we go to the right side of the max, and then we guess, and then the maximum is going to be 30, 1800. Now what is the 30? The 30, remember, is H, and the 1800 is area. So it says find the width of the base that makes the area of the cross-section a maximum. So we know that the maximum cross-section is 1800, and we know that the H of 30 makes it maximum. But what value of W makes it maximum? So we can find that with this equation here. We can put H in for, we can put 30 in for H, and then we get 120 minus 60 equals 60. So the width that makes it maximum is 60. And that is the end of this section.